Welcome, everybody. Thank you so much for coming out on this not rainy night, on a Monday night. I know this is not a night that one normally expects this kind of event to happen, but we're really thrilled that all of you have come out here tonight for this event. It means quite a lot to us. I'm Alan Christie. I'm an associate professor in the history department, and I'm the provost of Cowell College. Cowell College is the host of tonight's event. And I'm really thrilled to be the host of this event, which is a meeting of three highly accomplished people for a conversation about knowledge making in the modern world. You will have seen, I think, outside that we have books on sale, and we will have book signing afterwards and other things like that, but I'll be making an announcement about that at the appropriate time. But for now, what I'd like to do is introduce our chancellor for some words of welcome. George Blumenthal is a tireless champion of public higher education. He is a product of public universities, I want to stress that, with a BS from the University of Wisconsin-Milwaukee and a PhD from the University of California, San Diego. He came to UC Santa Cruz in 1972 and has been our chancellor since 2006, interim for 14 months and then permanent, well, not permanent, but full-time. Under his leadership, our campus has made real strides toward becoming the public institution that California needs, for he's been a champion of diversity in particular. Enrollments of underrepresented students have risen 50%. Nearly half of our incoming frosh receive Pell Grants, the federal grants for the neediest of students. And about 40% of our students are first generation, and we have become an Hispanic-serving institution. These are all real achievements, I think, for a public institution like ours, and I really want to applaud Chancellor Blumenthal for his leadership in that. And it's not just these enrollments. We have innovative programs in games and playable media, critical race and ethnic studies, and robotics, amongst many others. Chancellor Blumenthal has made sustainability a core value on our campus, from water conservation to local sourcing of food. And our relations with our Santa Cruz community are more productive and collaborative than at any time in my 22 years here on the campus. He has served the campus and broader public in many capacities, and we learned just last week that he has been named to the governing board of the California Institute for Regenerative Medicine. These are all significant achievements that are worth reflecting on, especially in the course of the conversation I hope we have tonight. And with that, I would like to invite our chancellor.
Thank you, Ellen. That was a very kind introduction. And welcome to all of you. Tonight we have an august group that we will be hearing from, and it's going to be, believe me, it's going to be a great evening. I'm delighted to see Ren Weschler again. He was here 2 years ago at Cowell College with Professor Emeritus of Literature, Art, and History, Harry Berger, and fellow Cowell College alum, Bill Finnegan, who, by the way, won a Pulitzer Prize this spring for his memoir about surfing, which is called Barbarian Days. I last saw Ren at Alumni Weekend during our tribute to John DeZikas, and also a tribute to teaching on campus. That weekend, Ren also led a discussion about his book, Domestic Scenes, with the subject artist Ramiro Gomez. Ren is actually a very, very prolific writer, propelled by his prodigious curiosity about the world around him. I like to think we can take a little bit of credit for that, for nurturing Ren's intellect while he was here at UC Santa Cruz as a student. And he's been kind enough to suggest that his professors were, in fact, influential in his life. One of the most striking aspects of Ren's career is how unbounded his curiosity is, writing about war and politics, torture and art. And a lot of it is about art. Our special guest tonight, Walter Murch, has a similarly active mind. He has spent decades exploring Bode's law, which you will hear a lot more about, a theory about the placement and movement of planets in the solar system. Now, I am an astrophysicist myself, But I am staying neutral tonight, just so you know. What is really impressive to me is the bond of intellectual curiosity that both Ren and Walter share with one another. And I can say the same for my friend and colleague, Enrico Ramirez-Ruiz. Enrico is an engaged, well-rounded scholar. And in addition to that, if he weren't an astrophysicist, I'd probably be calling him a humanist, because he brings amazing heart and tremendous breadth of knowledge to his work. So I know this is going to be a fascinating evening and a fascinating conversation. So let's get going. Thank you.
It's my first time hosting this kind of thing, so of course I forgot to tell you that he is the one man in this room most likely to understand tonight's conversation, besides the three guests. So I'm really glad that he's here and that I'm sitting next to him. Our event is made possible by many things, but I'd like to highlight at the start two things. First, we are here on the occasion of the publication of Ren Weschler's most recent book, Waves Passing in the Night, Walter Murch in the Land of the Astrophysicists. I'm so grateful that Ren proposed this event to me in the form we have it tonight, with our three speakers on stage tonight. We are also here thanks to an endowment at Cal College, the Siegfried Pucknett Fund, which was established in 1997 in the memory of a founding fellow of Cal College to support events bringing literary studies events to the campus and to the public. The event is also graciously sponsored by the Departments of Film and Digital Media and the Department of Astronomy and Astrophysics. Events like this one do not happen magically, as you know, but are the result of hard work by the skilled professionals in the Institute of Humanities Research, in special events, the development offices of the Physical and Biological Sciences, and the Division of Humanities. All of them have earned my thanks in multitudes. And finally, this being a Cal College-led event, I want to be sure to give due recognition to Alice Folkens, Cal's Academic Programs Coordinator, otherwise known as my assistant, without whom I would be frankly lost. So please, thank you very much, Alice. So the book that brings us here tonight to this conversation, Waves Passing in the Night, Walter Murch in the Land of the Astrophysicists, is about many things. It is the story of an intellectual friendship, a story about a man's passionate pursuit of a very difficult question, a story about the evolution over centuries of a field of science and its practitioners, a story of the uneasy relationship between amateurs and specialists, a story of acoustics and astrophysics and more. While the reader of this book will spend a lot of time with scientists and philosophers from the 17th, 18th, 19th, and 20th centuries, it is also very much a book for our particular moment in time. The bigger questions that this book invites us to contemplate about authority and the making of knowledge, about professionals and amateurs, and about the possibilities for discovering the new or rediscovering the new and the old are crucial questions for our moment, whatever discipline one may be pursuing in the academy or whatever questions one may wrestle with as a contemporary citizen. I don't think I need to say much more than the question of what is true feels really important right now. And I think the three people we have on stage with us tonight are exceptionally well equipped to model a public conversation about these questions. And I mean this seriously, modeling this conversation, because it's not necessarily going to be always an easy conversation, much like other conversations we have. I will begin quickly with the author of the book, Ren Weschler. Ren, if I may. Ren is a graduate of UC Santa Cruz, or to be more precise, as he says on his Wikipedia page, Cal College. Thank you. A longtime staff writer for The New Yorker, an essayist published in New York Times, Los Angeles Times, The Nation, Harper's Salon, and others. Ren is also the author of now 16 books. Do I have that right, 16? That neighborhood. I'm a historian, I don't have to count. Including one of my all-time favorites, Mr. Wilson's Cabinet of Wonder, Boggs, A Comedy of Value, Vermeer in Bosnia, Seeing is Forgetting the Name of the Thing One Sees, 30 Years of Conversations with Robert Irwin, and Everything That Rises, a book of convergences. One theme that emerges regularly in his work is the story of the artist who plays with and troubles the act of knowledge-making or the certainty of authority. Not an uncommon thing for artists to do. That is one of the things that we need them to do. But some of his artists, such as David Wilson and J.S.G. Boggs, push their projects to disorienting extremes. Take Wilson and his Museum of Jurassic Technology in Culver City. At his museum, Wilson creates elaborate, semi-true hoaxes in displays of natural historical objects and oddities, or maybe supernatural, in a kind of updated version of a Cabinet of Wonder. But these hoaxes, at least we're pretty sure they're hoaxes, are predicated on a practice of deep research and on excruciating fidelity to the conventions of expertise in academic science, at least of the kind practiced from the 19th century back. One finds oneself unwilling to believe the stories he tells or the objects he presents, but also unwilling to disbelieve because of his rigorous adherence to citation authority. J.S.G. Boggs produces hand-drawn reproductions of currency to exacting levels of precision, albeit with subtle changes that clearly show his money is not a forgery of actual government issue. In Boggs we trust, he writes on his bills. But then he attempts to live exclusively by spending his money, not in selling his art for money, which he then spends, but by convincing people to accept his money in return for goods and services. He seeks to convince people to treat his work as if it were money, always therefore playing with that sense of certainty and authority. But Ren's story of Walter Murch is not a story of the man trying to pass off a hoax or get people to act on his fabrications as if they are real, although Hans Weihinger's philosophy of as if plays an important role in this book. Rather, this is a story of a man of tremendous accomplishments in one field, pursuing a question that is not only native to an entirely different field, but one that field has already discarded. I fear mangling this, but I'll step into the minefield nonetheless. Murch became fascinated with an 18th century theory that he'll present to you about the location of planetary objects' orbits, known as the Titius Bode law, or Bode's law. In exploring the law, he further discovered that the intervals between planetary orbits predicted by Bode's law matched the intervals between notes in the musical scale. And with this observation, which Murch claims he was the first to notice, he brought to bear his expertise in sound design to his layman's fascination with astrophysics. But Murch faced at least two giant obstacles in his attempt to pursue the resonance he found. He was coming to the central questions as an outsider, without recognizable training or authority, and the theory he wanted to resurrect for reconsideration was one that the field had already dismissed as outdated. Getting professional astrophysicists to take him seriously was going to be a big hill to climb, and this book is about Murch climbing that hill. And so tonight, he's going to be joined by someone who will help him climb. Many in this audience know Walter Murch's work far better than I do. A graduate of the USC film program, Walter Murch came up to San Francisco with Francis Ford Coppola, George Lucas, and others to start the Zoetrope studio in San Francisco. While there, he built his gigantic reputation as a film editor and sound designer, working on such films as Lucas's THX 1138 and American Graffiti, and Coppola's The Conversation, The Godfather series, and Apocalypse Now. A stunning first decade of work, if you think about it, all done in his 30s. I'm 53, and it makes me intimidated. He has written and directed his own films, including Return to Oz, edited many others, such as Julia, The Unbearable Lightness of Being, The English Patient, The Talented Mr. Ripley, Cold Mountain Jarhead, etc. Murch has also given us a number of important innovations, including most famously his rule of 2.5, which he could discuss. Murch is also the author of one of the standards of film editing, In the Blink of an Eye, and essays such as Oblivion or Immortality, Dense Clarity, Clear Density, and the translator of The Bird That Swallowed Its Cage, the selected writings of Cruz Malpart. Our third guest tonight, Enrico Ramirez-Ruiz, is our youngest member, but is equally accomplished. As Professor Blumenthal mentioned, he is a professor in our Department of Astronomy and Astrophysics. He's also the Niels Bohr Professor at the Dark Cosmology Center at the Niels Bohr Institute in Copenhagen. He did his graduate work at the University of Cambridge in England and a postdoc at the Institute for Advanced Study at Princeton University, home of Albert Einstein and Kurt Gödel. His research, he once put it, is in extreme astronomy. He studies plasma in extreme astrophysical environments. He studies gamma ray bursts, supernova, compact binary evolution and dynamics, cosmology, and star formations in dense environments. He has received the Edward A. Boucher Award from the American Physical Society, a prestigious fellowship at the Radcliffe Institute for Advanced Study, and several other distinctions. He was also the lead in a recent art exhibit at the Cessnon Gallery called Black Hole. When Ren first contacted me to propose this event, he has asked that we bring an astrophysicist to join us on stage to talk about the book and Murch's quest, and I knew right away that Enrico was the ideal person to have join us. He's not just a brilliant scientist, he's also a brilliant storyteller and a model teacher. I think Enrico can speak to us in multiple registers and think through the big questions of the night from perspectives that we badly need. And so let me wrap up to restate quickly what those questions are. We're interested tonight in the question of the relationship of the amateur to the specialist, in the question of the creation of knowledge, the discovery of the new. This is a question of cross-pollination and authority. What do we owe each other? And just before, the last thing I want to say, because this is a Cal College hosted event, and I think this event very much speaks to Ren's experience of Cal College and my experience as I'm coming here now. Because this is very much about the conversation across disciplines, the search for knowledge in a contested, sometimes difficult relationship between amateurs and professionals. In 2013, Ren published an essay called Back to Kindergarten, a modest proposal for the college of the future. There's lots of things to say about the kindergarten movement there, but I also read the essay as an ode to his education at Cal College. He describes for this future college that he would like to design a core class that he calls Playground. And let me give you a couple quotes from that so you can get a sense. Every year for this class, 12 members of the faculty would be peeled off to run the core, a different 12 each year, chosen to reflect the widest possible range of disciplines, a musicologist, say, and a physicist, a political theorist, a climatologist, a classicist, a microbiologist, a historian of Islam, a sculptor, an information scientist, and an economist, and so forth. Key here would be the fact that in most cases, the faculty leaders of the sections wouldn't necessarily be any more conversant with the topic in question than his or her charges. He or she would just have a better sense of how to use the library, how to read, how to hone questions, etc. This is truly an ode to what the colleges were meant to be at UC Santa Cruz, and as the new provost of Cal College, I can say it remains a powerful description of our aspirations in the colleges here, even if we sometimes fall short in practice. It is in the colleges, baked into the DNA of UC Santa Cruz, that we find the unique potential of this campus within our great system of public education in California. That if we hold dear the possibility of the colleges as that place where the professional and the amateur can come together to explore and contend the process of knowledge making, we can create students who are truly public intellectuals. I think many would share my sense that we need these people in these times. So with that, I would like to invite first Walter Murch up to the stage to talk to us. All three of you coming up? All three of you, Walter and Ren and Enrico, please join us on the stage and join me in welcoming them.
Walter?
Okay.
I just wanted to come out a little bit to introduce Walter and say a few things about how we're going to do this. Walter, I've known now for over 20 years, and he is obviously, you've heard all about the films, and many here in the audience are here because he is revered for those films as well. He should be. But he's also a person of extraordinary breadth. The kind of thing he's going to do this evening is not the only kind of thing he does in his spare time. We'll talk about why he does it in a second. But just to give you some idea, I just want to give you a sense of Walter, because he's constantly reading in a whole wide variety of areas. And for the last 20 years, he's carried around this little pouch. And he will occasionally, whenever he's with anybody, he'll just say, here, reach in and take something. And it's all Chinese fortune cookies, only they're, the little, pieces of paper. Only they're quotations from his readings. And I just wanted to give you a sense of Walter's range. These are some of the ones that I picked up over the last several years. The great battles are always waged where the maps overlap. Napoleon. Translate the invisible wind by the water it sculpts in passing. Robert-Bresson. Tell the truth as you see it, let beauty take care of itself, Fred Zinnemann. Truth never comes into the world but like a bastard to the ignominy of the one who brought her forth, John Milton. If at first the idea is not absurd, then there's no hope for it. Einstein. Music is the pleasure the human soul experiences from counting without being aware that it is counting. Leibniz. Seek simplicity but distrust it. Alfred North Whitehead. Science is the belief in the ignorance of experts. Richard Feynman. Start every film with one certainty and a million questions, and end every film with a million certainties and one question. Walter Murch. I just wanted to give you a sense of that because the part of Walter that will be displayed this evening is just a small fraction of the whole, and it's been one of my great joys of the last 20 years to be able to hang out with him occasionally. In other versions of this, it's just been Walter and me, and Walter has a slide presentation that is just mesmerizing. It can go on for 45 minutes or an hour, but I have asked Walter to do a little compress of it for about 20 minutes, 25 minutes.
I will do my best.
And we will urge him on if he's not. And then the point is that I want to really come down and talk about, with Enrico, the point is to give you an idea of the kind of thing he's doing as, quote, an outsider, and then to talk about how it can work. Is that good?
All right.
Go, do it.
Thank you, everyone, and a special thanks to the audiovisual department who did heroic efforts at the last minute in getting all of this arranged. So, can you all hear me? Yes, okay, good. This is a drawing made in 1610 by Galileo. It's the first object seen by telescope invisible to the naked eye. And this is the planet Jupiter, the big circle, and then the four stars that as he called them, that orbited Jupiter. He gave them the names of lovers of Jupiter, and there's a mix of sexes here, which adds a little spice to the arrangement. About 400 years later, we took this picture of the romantically named star HR 8799. It's pretty close to us as far as galactic space goes. It's only 129 light years away. It's very young. It's only 30 million years old. And the names of the planets that we see orbiting are romantically named B, C, and D. But we are able, in this case, to actually see the planets. Exoplanets, as you may know, are rendered visible mostly by the effects they have on the central star, making it wobble a little bit, or by dimming the star as they pass in front of it. In this case, because of the gigantic size of this system, we were actually able to photograph it. The star really doesn't look like a Christmas ornament. This is a device they use simply to mask the effect of the star so that we can see the planets, which are much less bright than the star. In an idealized form, those orbits look something like this. The numbers you see there are what we call astronomical units. 1 astronomical unit is the distance from the sun to the Earth, so you can imagine how huge this system is. The C planet is roughly where Pluto is in our solar system, so the B planet is perhaps almost double the distance further out. But what's interesting to me about this is the proportions of the orbits, these idealized circular orbits. Orbits, as we know, mostly are elliptical, but for the purposes of the diagram, I've made them into circles. But if we superimpose Galileo's moons over the moons of HR 8799, we find that there's a high degree of congruence between those 4 orbits, even though the Jupiter orbits, the moons of Jupiter, are 5,000 times less, 5,000 times smaller than the orbits of these planets. So these numbers that you see under there are also in astronomical units. And to add another layer to the cake, we can also superimpose the orbits, in this case, of Earth, Mars, and Ceres, who are somewhere in between in terms of size. The orbits of, so the question is, what's causing this congruence of 3 very, very different systems? I selected these not quite at random, but almost, just to give an illustration of the kind of things we're going to be talking about. A very useful word is this apophenia, which is the tendency of human beings to see patterns where none exist. If you make breakfast tomorrow morning and see Jesus' face in an English muffin, you are having an apophenic moment. So I'm aware of the danger of pushing things too far. On the other hand, properly controlled, apophenia is at the heart of science because it's all about seeing patterns where superficially there don't seem to be any patterns. I should add that it's also inherent in filmmaking, that especially in editing, where we're looking for these deeper patterns to things. So this is just a cautionary note about things. Here's our apopheniac candidate number 1. His real name was Johann Dietz. He was German. In those days, 250 years ago, when you got your PhD, you Latinized your name. So he became Johann Titius because everyone wrote in Latin scientific papers. Copernicus was really Copernic, but when he got his doctorate, he became Copernicus. And Titius made the observation that if you start with a doubling series, 1, 2, 4, 8, and so on, and just for the hell of it, you start with 0, which we'll talk about in a sec, and then you take these numbers and multiply by 3, as we are all wont to do, add 4 to them, and then top it off by dividing by 10, we get a series of numbers, and though that series is uncannily close to the relative distances of the naked eye planets from the sun, with one exception, which is this blank spot with question mark there. Somewhere between Mars and Jupiter, this system said there should be something here. Titius himself said, would the good Lord have left this space empty? No. Astronomers, train your telescopes at this space and we will discover something. Titius was a relatively obscure professor. Johann Bode, on the other hand, was the Neil deGrasse Tyson of his time, a great popularizer, also a great astronomer. And he picked up what Titius had written, and he formalized it into what we might say sort of 9th grade mathematics, to something that looks a little less like a recipe that Julia Child might have come up with. The 2 in this formula is raised to various integer powers by the definition here, minus infinity, 0, 1, 2, 3, 4. And I'll put a little asterisk next to minus infinity because there's something peculiar about that as well. That remained a curiosity, but everyone sat up straight in about 20 years later when Herschel, the German-British astronomer and composer, discovered the planet, to the delight of 7th grade boys everywhere, Uranus, followed 20 years later by an Italian astronomer, Piazzi, who discovered the center of what we now know as the center of the asteroid belt, Ceres. And these are the first telescopic planets ever discovered. Until this point, everything we knew about planets was naked eye planets, and now we begin this voyage into telescopic planets. So here's a spreadsheet of the solar system the way it was when Titius and Bode were doing their thing, but by the end of the century, two new objects had slotted themselves in very neatly into places that were just simply waiting for them. And at this point, people just sort of rolled over and said, well, it's got to be a law, because it was both descriptive of what we knew at the time, but it was also inherently predictive of things that we might discover, and sure enough, when we discovered them, they fit. And popularly, it was known as Bode's law, although technically it should be known as the Titius Bode law. And for a number of years, it lived in this scientific heaven. Here was a living scientist who had a law named after him, Bode's law. And naturally, the curious minds wanted to go further. This newly discovered planet, Uranus, had some wobbles to it that made people think there must be a planet further out. So naturally, they began looking at the next iteration of the law. There must be something there. And Neptune was discovered in the middle of the 19th century by a French mathematician, astronomer, but it occurred much too far inward from where it should have been. And at this point, Bode's law lost the name law, and it became a long, meandering descent into oblivion, such that this Neptune didn't fit by an order of magnitude, and the law was so forgotten that by the time Pluto was discovered, nobody happened to comment that Pluto actually fit where Neptune was supposed to fit. So on encountering this, all this information in my reading, I thought, well, 9 out of 10 isn't bad. Why don't we give the benefit of the doubt, I'm just talking to myself here, and say, let's say that for some reason Neptune is a renegade, and we need to send him into detention, close the door, and we'll come back to him at a later time once we've examined this system and other systems to see if there's some pattern there. So Neptune went into the bad boys' room, and we will encounter him later. Carl Gauss was the Mozart of mathematics in the 19th century. He was instrumental in describing the orbit of Ceres, because Piazzi had only observed 3 days before Ceres fell into the brilliance of the sun, so he had very little data, and Gauss, as a young man, developed the system of least squares, which was capable of describing the entire orbit from very few data points. So he knew about Bode's law, and he had some caustic things to say about it. The first one was, what is that jump doing there? Why do you jump from minus infinity to 0? That is mathematically very suspect. So picking up that particular ball, I thought, well, what if we just removed it? Instead of that jump, we'll make it no jump, and we can go from minus infinity to plus infinity, a kind of heady experience thinking of this double infinity, but let's see what happens. Once you do that, the picture changes. These are the orbits predicted by the original Bode's law. There's the Earth orbit, the third rock from the sun. But the new formula shows a geometric progression or descent down to a limit, and it stops at that limit. So there's the old formula and the new formula. A close-up look at this shows these, what you might call virtual orbits, that are predicted by the law, but in our solar system are empty. Now, when we go to other systems, are we going to find that these orbits are in fact occupied? Perhaps we will. So that's a good, interesting test. The other thing that Gauss said was, what are all these weird numbers doing for a system that at that time had only 8 objects in it? If you allow me, Gauss said, to make a formula with 4 arbitrary constants and only 8 objects, I can choose and I can make anything fit. So he said, you should find a way to reduce the number of arbitrary constants. Here's the law, the orbits looked at on the side, and you'll notice that the Earth is, by the definition of the formula, defined as 1. So it's the standard of measurement for everything else. Mercury, for instance, is defined by the formula as 40% of Earth's orbit. Venus is defined as 70%. But isn't it peculiar to do that in the middle of a geometric series to make something the standard by which you judge the series? Let's change it so that we have the start be the thing that defines the whole series. So just turn Mercury into 1, and then through very simple mathematics, Earth becomes 2.5 times Mercury's predicted orbit. And if you do that, if you multiply that formula, Bode's formula, by 2.5, you come up with something that's simpler. And because we have made n into an infinite series, we are permitted to drop the -2 and just say n. If we hadn't removed the jump, we couldn't have done that. So that's the end of any complicated mathematics in this. To allow you to relax a little bit, here's a musical interlude whose intention will become obvious in a second. Music is all about number of vibrations per second. In our system, 330 vibrations per second, we call the note E, and it sounds like that. A higher note, and we can play those notes together. And we get the interval whose ratio of the two notes is 1.1 to 1.6. We can represent that graphically if we imagine a circle of radius 330 and a bigger circle, radius 528. We can have another circle. We can have many different circles. Here's one whose ratio is 1.25. At this point, something began to be familiar to me because of my experience mixing soundtracks. Here's that same orbit seen from the side. If you remove the sun, you're left with a geometric series starting infinitely close together and getting longer, intervals getting longer and longer. If we assign these numbers to it, 440 being the note A, we simply have the musical scale. And the formula for the octaves of any note are that note multiplied by 2 raised to the power of n being all integers from -infinity to +infinity. So here is a small sample of that. Here are 4 circles. And those are the distances of the moons Jupiter, of the 4 moons of Jupiter, Io, Europa, Ganymede, and Callisto, translated into vibrations per second. I've assigned these notes. We could have done a different scale, like transposing from one scale to another. On the piano, I happen to choose these. The important thing is the ratio of the intervals in that. And if anyone ever asks you, what do the moons of Jupiter sound like relative to each other? That's what they sound like. In fact, we can do the same thing for Bode's law's predictions of the solar system. And then all of this together. A way of making some visual sense of this is to imagine a statistical wave starting at a certain distance from the sun, and the formula that I just laid out predicts the troughs of this statistical wave. The simpler version of this formula, just without the 3 involved, predicts the peaks of these statistical waves, and the planets will nest into the troughs of these statistical waves, and they will avoid the peaks of these statistical waves. Whether this has any physical reality, obviously not in the two-dimensional form that I'm showing it here, is something that we'll discuss later, that Ren goes into in the book. Very interesting, provocative stuff. The other problem that Gauss said is you have to look at other systems to make sure that this law is not just a fluke. So let's look at the moon systems of Jupiter. These are the 4 moons that Galileo discovered, but we now know that Jupiter is surrounded by many other moons, a kind of a cat's cradle of 63 moons, many of them very small, but there they are. For the purposes of cutting through the underbrush, just to get a sense of the landscape, I am going to restrict myself to talking about moons that are 200 kilometers in diameter and up. So relative to the size of Jupiter on the left, that dot is a 200-kilometer moon. And Galileo's 4 moons look like that in size, and just to give you a size of the Earth relative to that, and here is our moon relative to the moons of Jupiter. It turns out that the 3 moons, Europa, Ganymede, and Callisto, fit Bode's law to this high degree of precision, 100.03, 99.71, 100.27. There's a moon missing, which we'll see in a minute. They are, Europa, Ganymede, and Callisto are in the Earth-Mars Ceres equivalent orbit. And Io is a renegade. It doesn't fit. In fact, it falls midway between 2 predicted orbits. And we're going to add it to our list of renegades. Neptune has a little companion in the detention hall. But when we go out to Saturn, what we discover is that a number of moons fit Bode's law, and even more interesting, we start to see these virtual orbits being occupied. So the moon Dione is in the Venus equivalent orbit, but Tethys and Enceladus occupy orbits which are predicted but empty in the solar system with this kind of precision on the numbers on the right. And when we go to the moons of Uranus, we get Miranda falling into another predicted but empty orbit in the solar system with this kind of precision. If we lower the threshold and talk about moons less than 200 kilometers, the Saturn's inner moons line up with this kind of precision, and Uranus's inner moons with similar precision. And if we look at all of the 200-kilometer and up objects, we get a 75% agreement with Titius Bode. What's curious to me, I certainly didn't go looking for this, is that each orbital system has an object in the Earth equivalent orbit. I have some intuitions about why this may be, which we may get into later, but it's another note of curious. And here are the 9 out of the 36 that don't fit. Let's look and see if there's some commonality there. Here are the ones that do fit around an idealized node. There's a technical term for this, which I'm forgetting at the moment. But Venus and Mars are at like 3.5% off, and the other ones are nesting right around where they should be. And here are the moons that agree with Bode, doing their nesting. And here are the renegades, and it turns out that 5 of them nest around the midway mark. I don't know what to make of this. I also have some ideas that we can talk about. There's Io. If we allow this midpoint to happen, it agrees at 100.45. I think we mentioned earlier that Io and Europa are in resonant orbit. Io goes around 2 times for every 1 time that Europa goes around. That also applies to Europa and Ganymede. So of the 9 renegades, 4 are still, they don't show up as a cluster. To see where they show up is something like this. So this is a difference between the 18th and 19th century idea of Bode's law, which was a model of clockwork precision, that the orbits were predicted, and as Titius said, would the good Lord have left this empty? No. Therefore, there must be something there. And if something like Neptune is in the wrong place, then the clockwork precision of the solar system is defective, according to Bode's law, and we have to throw Bode's law out because it's like a clock with a gear that is much too small for what it is trying to deliver. Whereas now, what we're looking at, now that we have all of these data points of exoplanets and huge data on the moons in our solar system, we can see perhaps that what we're looking at is a more statistical approach, that we're not saying that every orbit must be occupied. We're not even saying that there are some orbits that are statistically off, like Neptune. But looked at collectively, there is a tendency for things to fall into the pattern as described by Bode's law. One of the other things that I realized in doing it is that what Titius and Bode had done, perhaps without even realizing it, is that they had tailored their formula to the peculiarities of the solar system, which was the only system they knew with any thoroughness. There is a gap between Venus and Mercury, and they immortalized that gap by making a mathematical jump to sort of fit the facts. And also, because we live on Earth and we like to think we're special, Earth was given the unitary value to which everything else was compared, which made the formula more clumsy than it had to be. If we simply start at the beginning of the geometric series, then the formula relaxes. Once those 2 things were done, then that allowed me to extend it to these other orbital systems without having to rub up against these inherent contradictions. The other peculiarity of Bode's law is that any scientific article with the words Bode or Titius Bode in it, submitted to a serious physical review paper, would be put immediately in the trash can. And history was made a couple of years ago by these two astronomers at the Australian National University, who submitted a paper based on the Kepler data analyzing exoplanets and applying Bode's law to exoplanets. Here's Kepler. And here is the paper that they submitted, and which was printed in the the Bulletin of the Royal Astronomical Society, with these radioactive words, Titius Bode. And what they discovered is that of the 67 four-planet or greater systems that they looked at, they found a 96% congruence with Bode's law. Their law is different than mine. It has this essential exponential function in it. The A value, that's by comparison, that's mine, it's sort of the equivalent of my beta point. That's where they begin. The innermost planet is where it begins. And then C, they allow to be tailored experimentally for each system. So they have more wiggle room than my formula does. And that's the exponents are 0, just the positive integers starting with 0. So there's much more in the book about all of this, and very interesting side lights from this. But that's a general picture of of what I've been doing for the last 2 decades in between films. It's a fascinating way of refreshing myself, going from the chaos, or the relative chaos of filmmaking, into this other world where things are, the timeline is much, much longer. Yet the commonality of both is the search for patterns. As I said earlier, the film editor, one of his obligations, his or her obligations, is to look for patterns at the most superficial level. You know, does she pick up the glass with her left hand or her right hand in each shot, to deeper and deeper levels, hopefully in the end, the most basic level that arcs throughout the whole film. And astronomy, obviously, since time immemorial, is about looking at the apparent chaos of the stars and finding deeper and deeper patterns in it. So let's welcome our 2 other co-conspirators here and continue the discussion.
I really, is this on? Yeah.
Yep.
I really scolded him backstage. You have to make it fast, you have to make it fast. And he left out some really good stuff. Yeah, we can turn off the formulas up there. But that's pretty fast. Just the way the book works is that the first part is a profile of Walter and of his theory and of Titius Bode and all this kind of thing. And the second part, and it ends with him saying, you know, something seems to be going on. At least it's worth entertaining. And part 2 begins, astrophysicists were not in an entertaining mood. And it follows the kind of thing where I go around looking for astrophysicists who will talk to us. It's interesting, by the way, Lineweaver, we didn't even try Lineweaver and Bovaird, because the last thing they needed to support them, they were involved in a huge controversy with what even mentioning it at all. And the last thing they needed was an outsider like him showing up. So
Talking about music of the spheres.
Yeah, they did not want that. So, but I contacted all kinds of people, and it became, for me anyway, fascinating. As you read it, it kind of goes in waves. The first person who comments, astrophysicists, you say, oh, he must be wrong. Obviously he's wrong. Oh, maybe he's right because he answers it. And it goes back and forth, and it gets wider and wider in terms of waves of believing he's right, he's not right, he's not right, he's not right. But there's more, for me, much more interesting stuff, which is basically, for starters, we mentioned, for starters, the problem of who gets to take part in this conversation. Over and over again, we were told, if Walter will just write this up as a peer-reviewed paper, we'll look at it. And the whole point is Walter very consciously says he doesn't know how to do a peer review. He'd like to work with people, like to talk to people, and he was having trouble. And so just at the very beginning, the notion of outsiders and insiders, the caste system and so forth came up. And one of the things I love about Cowell and I love about Santa Cruz in principle is that in the conversations with the chancellor and also with others, I had the sense that this might be a place where we really could have a little bit more of a conversation. And I don't want to turn this into, I really don't want to have it be a debate, is he right, is he wrong, but just what does science make of somebody like this? And what value, well, let me start with that, and maybe...
I should, before we get into it, I should say that I'm not, raging, rattling the bars of my cage in frustration at this. I've been perfectly happy doing this. I would like to extend the conversation, but I'm furthest from being actively frustrated by any of this, and I'm just very happy going down my particular rabbit hole, learning all kinds of things as I went along.
Yeah. No. Can you hear me? Yes. So, I think some of the overall, rejection that some of these ideas get come from the fact that our theory of gravity is so precise. And I'll tell you about our failures as an astrophysicist in actually explaining the architecture of planets and how all of these insights are really deep and can actually teach us something really deep about how planets are made. So, we can predict the motions of planets with precision, which is, the size of my hair in, the orbit of the Earth, with that amount of accuracy. And of course, from some of the physicists, when they see, 3% accuracy, and then you throw, 9 out of the 36, people start getting worried that it's no longer a predictive theory. However, there's something really deep about this, which is that astrophysics cannot really explain why planets have the current architecture that they have. In other words, and I think what Walter's really pointed at is that planets do not just simply randomly choose, their positions. There's basically very intricate physics that go along as to how they get their positions and ultimately how they survive those positions. So just to give you a feeling, a lot of these planetary systems, the planets interact with each other. So you really want to have planets not very close to each other because otherwise they will kick each other out from those orbits. So when we think about a planetary system, we think about, is this planet stable? Is this planetary system stable? And is it stable enough that we can see it over the lifetime of the universe? And that's a very important question. So there's certainly a very important selection effect of the planetary systems that we see. And I think Walter really alluded to the fact that those planets are not arranged randomly. And there's a pattern emerging, and the question is, can we deeply from the laws of gravitation explain that pattern? Is it exactly the pattern that we're putting forward as these geometrical law? I mean, there's arguments as to why is it that the law is actually exponential or has these logarithmic divergence, and this is because planets don't want to affect each other, they want to be stable, and that...
I, by the way, as a writer, love the language of intentionality here.
Yeah.
What do they choose? They don't want, and I just pointed out that we're talking in metaphors. We
are, because of course, if you start a system in any configuration, ultimately it will either drive itself to a configuration that is stable, or it will basically dissolve. no? And a lot of the interesting sort of discussions that I've seen about this paper statistically is, have they actually done, correct the statistical
This is the
test,
Lineweaver
the
paper.
Lineweaver? Have they actually taken into account that we're not sensitive to see all the planets, because of course the smaller planets are much more difficult to see. But I actually do think, and after I read that, Walter and I sort of decided that this has to be tested in a configuration that, we now, as, when I was talking to George, he says, well, we have all the tools to do this test effectively and really think about what are the stable patterns that emerge when you try to make any planetary system of any composition. What are the planets that emerge and how close to this, beautiful sequence of orbits are they? So I think it's because a little bit of the discussion is that in physics, you want to be not 88% right, 75% right. You always want to be perfectly accurate. And if the theory is not perfectly accurate, there's some deviations that are telling you something interesting about new physics. And that's, of course, how Newton's law got disrupted by general relativity.
On the other hand, I would say that imagine yourself driving down a field somewhere in the Midwest, and you pass a field of sunflowers. 10,000 sunflowers are looking back at you with their big round eye, and what hits you viscerally from that is roundness, circularity. On the other hand, if you then stopped your car and got out and wandered among the field of sunflowers, measuring the actual circularity of these sunflowers, you would find that none of them were really circular. They're trying to be circular, but the exigencies of the particular way that they grew, the fact that they didn't get enough water in May, and the fact that some toxic cloud blew over them in June, and that July was too hot, causes the desire, the urge to be circular, to have to be compromised somehow. But there's no question that we would understand in the DNA of the sunflower is a command buried somewhere to become as circular as you possibly can.
How would you describe, why do you think there is the 2% deviation, 1.8% deviation, and so forth?
Well, certainly when we're talking about the electron orbits around atoms, we are talking about very precise angstrom units, but here we're talking about macro systems that are subject, just like the sunflowers, to all kinds of disruptions. Uranus, our friendly planet, is rotating on its side. Something happened there. Venus is rotating upside down. The moon Triton in Neptune is retrograde. It's going in the opposite direction from everything else. So in any macro system, there are all kinds of disruptions from things that we know about and also things that we don't yet know about.
But for example, the one that's going opposite with Triton, did you say?
Yeah.
Yeah. Is it in about our orbit, even though it's going?
No.
It's the one that's not in about
Right.
orbit. Yeah, right.
Right.
So something came along,
Right.
and is it also possible? I'm curious. I had never thought about this. That something that's 1.6% off today in a million years might be 1.3%, and it might then go the other side.
There are things called digital orreries where we enter in the masses of the planets and their particular orbits, and then on a supercomputer you just crank it up and go hundreds of thousands, I guess, maybe millions of years into the future or the past, and what we see are the planets doing a kind of dance. What is curious is that they stay within certain bounds. They don't go this way in the digital orrery, but they don't stay exactly where they are. There's a mutual influence at work,
Sure.
and what we're looking at now, clearly, is a snapshot of something that has existed for 4.5 billion years.
But the intrinsic sort of phenomena there is that we're inputting the laws of gravitation and evolving the systems, no? So there's the fundamental law that is driving the orbits and is basically making the interactions, that then all of a sudden those laws arrange them in those architectures. No? So it's not that the architectures are telling them, okay, you have to sit here. It's really the dynamical influence of the two-body interaction, which we know it's very accurate.
The two bodies being?
All the multiple bodies.
Right, okay.
Everything attracts each other. And we know basically the constant of interaction of that law very, very precisely. And just by saying, force equal, mass
Right.
multiplied by acceleration, and you let that go in a supercomputer, these orbits and patterns emerge. No? And
If you were to put force equals mass times acceleration into a computer, would you get musical octaves?
So that's the very interesting question that I think I would like to explore. How often do you get that? No, the problem is of course the initial conditions. No, so what planetary scientists are debating a lot is how does these objects grew? They all form from a disk. This is a culture gravity is a culture in which if you're a little rich to begin with, you become even wealthier because, those objects that started slightly more bigger become bigger and bigger and they start forming. They start clearing up the gas from its surroundings, so there's a hierarchy.
By drawing stuff into them.
In the drawing. And then ultimately they sort of have to arrange in an architecture in which they eject the debris in between them, all of the material that was not lucky enough to grow into something bigger gets ejected into the solar system, and then those are sort of like the initial conditions. And then from those, you do F equal ma, you basically solve the force of every single object against everything else, you evolve, and then you look at what systems are stable and what systems are not. Now, in addition, we know, and you show the moons of Jupiter, that there are other effects, like tidal interactions, that arrange them in these resonant states,
So describe what you mean by resonant.
Resonant states is states in which actually the periods are integral multiples of each other.
So if one goes twice around the star,
The other one can go once, or the other one can go four times.
right? But only 3 of them do that. The fourth
Yes.
one doesn't.
Yes.
What's your point about that?
Callisto, the
Right.
furthest out of the Jupiter orbits, lunar orbits, is not in a 2-to-1 ratio. I think it's in a 2-3-3-3 ratio. But that original diagram that I showed at the beginning shows this grouping of HR 8799 with those 4 planets, and then superimposing Jupiter's moons on it. They line up with a little wiggle room, and then Earth, Mars, and Ceres line up with also a little wiggle room. The only objects in any of those that have a 2-to-1 ratio are Io, Europa, and Ganymede. The planets of HR 799 are, the first 2 are in a 1.9 temporal ratio, the next 2 are in a 2.2 temporal ratio. And yet, they line up in these troughs, these statistical troughs, so to speak.
And for example, in resonance, we know that has to do with the distance to the central object. Because the closer you are, the more basically the gradient of the gravity between one side and the other one of the object tends to align them in those orbits. Now, we see lots of planets in in 2-to-1, 3-to-1 resonance, and there's a huge amount of debate within the community of how they got to be in those stages. Because of course, being in resonance is actually a destabilizing effect, particularly with massive bodies, because that means that there's a non-negligible probability that they will pass very close to each other and alter their orbits.
Because this one's going like this and this one's going like this, but they keep on passing right next to each other, that they could be messing each other up and throwing themselves out of that, or what happens? And is that what we just see them for right now that they're in the right?
They could, and then you can calculate how long that system will be stable, and the answer is not very long, though. I mean, millions of years, but
right.
not compared to billions of years.
You remind me of my kindergarten teacher, where she said one day, in a million years. She said, in a billion years, the sun is going to explode and destroy the earth. And little Johnny in the back there said, "What did you say?" And she said, "In a billion." Oh, thank God! I thought you said a million years. but
What was the Woody Allen joke about the homework?
How's it go? I forget.
It was something to do with
A similar sort of thing.
thinking about the destruction of the solar system.
Yeah, so why do
and
homework?
why would I bother to do my homework?
Right. But But anyway, but I guess what interests me hearing both of these things is it'd be interesting to talk about notes wanting to be in pleasing places, in the way you talk about planets wanting to achieve a certain kind of orbit.
Or stable,
Yeah.
Maybe
I mean,
the melodies that are in those places are the only ones that survive.
Well,
Yeah, well, I mean, if you look at notes that are harmonically related, you find this, that diagram I had of the troughs
Right.
and crests. What you'll find is that the waveforms of those notes kind of nest within each other very neatly. And for some biological or neurological reason, that nesting perhaps resonates with some part of the architecture of our brains. It certainly relates to the behavior of objects according to the harmonic series, which happens musically whether they're human beings or not. Birds sing according to this system, and an object struck by a meteorite on the surface of Mars would resonate at a dominant frequency. It would also resonate an octave higher, and which is 2 times, and then it would also resonate 3 times higher, 4 times higher, 5 times higher, and by doing that, you generate the notes C, C, G, C, E, G, B flat, C, which is what we're seeing in these orbits.
by the way, you mentioned musically it's a 7th chord? Or,
Yeah, C, E, G, B flat, C is the 7th chord, so-called.
which is what we're seeing up here. Which is the jazz chord. It's
Which is a jazzy chord, yeah. For many years, if you were somebody writing music in the 18th century, you would avoid that because it was not considered to be a pleasant sound. But there's all kinds of articles online about some black hole that resonated at B flat. So who knows?
I guess let me ask you a question in this sense. And this is I want you two later on to go somewhere and, you go outside and work this out between yourselves. But what I do want to ask is it possible that, we will say for the sake of discussion that Walter is every bit as much an acoustician as astrophysicists or astrophysicists. He is at the top of his profession. And if anybody was going to notice a pattern like that, it would be Walter, and that he would have a metaphor for it, which would be a wave thing with troughs and things, and that it's not necessarily the metaphor that's being used in astrophysics today, but there might be a way. It would be by definition an outsider who was not trained completely in the disciplines and the metaphors of the discipline that would have a new metaphor and might notice things that were of interest. I mean, is that a fair way of thinking about how science goes forward and the role of outsiders and so forth?
I think it's very interesting that people within the planetary community haven't even really thoughtfully asked, is the architecture of planets just a random realization, or is the fact that you need orbits to survive, leads to some attractors that basically prefer certain patterns. No? And I feel like you're absolutely right. Science is all about finding patterns and explaining those patterns. And, we need people like Walter. We need people that have a fresh perspective of saying, this is quite interesting. It's not, you guys have to pay attention to this and you have to explain why this is the case, rather than just this tendency of being dismissive to the outside and say, we understand everything, which we don't. No, we really don't understand why planets have that architecture. So no one in good, standing can just say, there's nothing to it. It is clear that there's a pattern. We don't know if it's the exact pattern, the one that he described, but it is clearly they're not random. And no, I feel that we need those sort of conversations. We need to engage scientists in thinking about, what they've been taught for, centuries, and trying to think about, well, is there something to it? Can you actually explain it to me? Or can you disprove it in a way that, it's mathematically rigorous? And I think these sort of idea, rather than us having to work it out outside and trying to convince each other. We're just actually going to use the tools that we have at our disposal, and we're going to actually find the answer in a statistical, mathematical way, and that's possible. No? And so,
I'm just curious, if it were to turn out after your statistical study and so forth that there was something really uncannily, quote, musical, and by the way, we have to make absolutely clear, we're not talking like you can go outside and hear music. These are the ratio of distances. This is statistical music. But if it were to come out after you've done the statistical, that there was some kind of resonance with musical octaves, A, would that blow your mind, and B, would it be exciting? I mean,
well, I mean, I think anyone sitting hearing to Walter, it's already, amazed that you can actually relate something as, the distance in planets with this beautiful music. I mean, it's something that, those analogies are the ones that actually make science thrive and makes it effective for scientists to communicate with the public, and looking at patterns in nature, looking at, I think you have in your book this beautiful picture of the neural network and dark matter network.
This is, by the way, really mind-blowing. Let's time out. Walter one day sends me a picture of galaxy, that's just been recently done, of how galaxies play out in neural networks, and he puts it side by side with a picture of how a mouse's brain at the micro level looks at the macro level, the micro level, and they're basically almost the same thing. Which he then follows up by, and real time out here, but I'm just going to say this very fast. Walter is the kind of guy who gets in his car in Bolinas, drives to San Francisco to his editing bay, and asks himself, on a per volume basis, which emits the most energy, the human brain or the sun? First of all, who asks themselves a question like that? But secondly, he figures it out while he's driving, figuring it out in his head. And if you were to take you'll have to look up in the book why this is true, but if you were to take a brain-sized quantity of sun, on average, of the whole sun,
A Cuisinarted sun,
take out and compare it to a brain, it turns out, he figures out by the time he pulls into his parking space in San Francisco, that the human brain emits 56,000 times more energy than the sun. Now, I mean, as one of the people I talked to afterwards says, well, his does, but there's various reasons, and you ought to read about it in the book. But these kinds of ways of, I mean, that's not the kind of question I would expect a scientist to ask.
I actually spent quite a bit last night thinking about that question myself, and thinking about. Anyway, I have a different perspective on that question, because it's really a question between, but I won't go into detail. We can talk about it at dinner. But it's a question between the area to volume ratio.
Right.
So when you compare those, for example, I mean, we all humans are at the same temperature, but for example, babies have a much larger area than they have, volume. And that's why when people tell you, put a hat on a baby, most of the surface comes from from their head, is because they actually radiate significantly amount more energy per unit volume.
Yeah, each of us on average is like a 100-watt light bulb, 24 hours a day on, but our brain is 20% of that. So the brain is emitting 20 watts of energy compared to the 100 watts for the rest of the body.
And for babies, it's even higher.
And babies are higher.
But anyway, we
won't go into the details here, but I guess the wider question I'd ask you and I'd ask you is what is the value of art and science talking to each other, or of people of different kinds of sensibilities talking to each other and savoring the conversation? And I know that you actually teach a class. Talk about the class you teach about Newton.
Yeah, I mean, I would say that my interaction with scientists, and I've been working a lot with Jennifer Parker in this open lab collaboration between science and artists, it's really that artists get to ask you questions that scientists don't get to ask, that sometimes go to the root of the problem and make you think and re-envision the way that you approach science. They also are great at looking at patterns and seeing patterns. We do these 3D computer simulations, And, you can show that to an artist and they will look at slight difference. I remember we wrote a paper just basically based on the fact that, when a star gets very close to a black hole, it gets disrupted and you create sort of two tails that break apart. We showed these movies and, the perception was almost like 1 part in a million. And one of the artists says, well, but the tail coming in this direction is actually different to the tail coming on the other direction. I'm like, yes, you're right, 1 part in a million. We measure it, and it is true that you can actually see. So someone can actually saw this, and then we say, well, the fact that you eject, 2 different components on mass, that means that in order for momentum to be conserved, the star is actually going to move. And so we started thinking about kicks through those interactions. But that was basically an artist realizing, just by looking at the movie, that there was a discrepancy of 1 part in a million by eye. So those sort of interactions are amazing. And also as scientists, we're trained in some ways that, these are the foundation of science that you're not really supposed to argue against, and then you build on top of it. While, artists are irreverent, and they say, well, what are those the foundations? Teach me. And I think that conversation is something that we really need. We need people that are not almost in a doctrine way of thinking and envision science to really challenge those beliefs and, scientists to be open-minded or to feel vulnerable enough, because a lot of times you say, well, you know what, I always assumed that was true and I have never really challenged that perspective of science. So let me get back to you.
There's a wonderful observation by James Baldwin who said, art asks the questions that have been hidden by the answers.
Art uncovers the questions that have been occluded by the answers.
Okay, more exactly.
Says the writer.
And by the way, I'm going to offer you an observation of the great, great butterfly scientist, lepidopterist, a Russian butterfly scientist, not very well known, named Vladimir Nabokov, who said that the true master has the imagination of the scientist and the precision of the poet. But coming back to you, I mean, it's not as though you are saying science is horrible. I mean, all you do is read science all the time,
right,
and you revere science.
Yeah, absolutely. There's a wonderful diagram in a book published by Charles Simonyi of his father's physics textbook, and he plots side by side progress in science and progress in the arts over a 5,000-year period, as near as we can tell from the evidence that we have. And the two of them do a very interesting sinusoidal dance, that art bulges, meaning it does a lot of stuff, and then science bulges afterwards. And then art bulges and science bulges. And it relates to what you just said, in the sense that art can break up the earth, in a sense. It can plow over the earth of hidden assumptions so that science can, a new kind of understanding of the world can grow out of that. So they have different ways of approaching, almost sequentially, the problems of how does culture establish itself, and then how does culture progress.
Let me ask you a question. If Walter comes to the cafeteria in the Astrophysics building, is there a cafeteria these days? I don't know. Anyway, will he be sitting by himself, or will everybody want to talk to him?
Everyone wants to talk to him.
Really?
No.
I mean, seriously? Because that wasn't true of the cafeteria in my book. Nobody will talk to him.
I would invite him to give a discussion at our coffee, and
Right.
I think he will be. I think there's lots of deep questions that his work is really bringing to the forefront that people have to think about carefully. And I think as scientists, you have to embrace. And if we're not able to actually show that these law, doesn't arise naturally from the laws that we know, and there's something else, then there's new physics to be found, and that's what we're all about. No?
There's another aspect that's interesting to think about, which is that Kepler, who accepted Copernicus's establishment of the solar system, of the sun in the center, Kepler, with great precision, long before telescopes, established that the orbits were elliptical. And this bothered him. In his book, he called them a cartload of dung, The fact because he couldn't figure out why God would have made elliptical orbits. He accepted the fact that they were. It was based on Tycho Brahe's observations, which were the state of the art at the time, but he punted the idea of elliptical orbits as, I don't know. He produced a series of astronomical tables, the Rudolphine tables, which were an order of magnitude more accurate than anything that happened before, and they were very useful. But why would this be? And this was a question that bedeviled the entire 17th century until Newton came along and said, at the end of the century, it's because of universal gravitation. And he had this very neat formula which we use still today. But Newton couldn't explain why gravity worked. In Latin, because they were all writing in Latin, he said, non fingo hypothesi, I do not make a hypothesis about how can one object over the remoteness of space influence another object. I don't know how it happens, but here is how it works. I don't know why it works. So he kicked the can downstream for another 200 and what years. Along came Einstein, another genius, who said, well, actually it's because of the distortion of space-time that we see gravitational effects. And Einstein, coincidentally, with the photonic effect, proved that, in fact, the quantum mechanics was real, Planck's hypothesis, but nobody knows why that is. And Richard Feynman, as per that quote, famously said, I can say with some assurance that nobody understands quantum mechanics. So there's always this dance of utility and understanding and utility understanding, and they are not coincident.
Yeah, it's almost like they're in a trough, but they're not quite at the center point, and they're kind of bouncing around each other and so forth. I can see that we're being called to order here. Alan has a few things he's going to say, but I just before that, I want to say something. First of all, to thank both of you. We will stick around here, so if you have questions you want to, I would have liked to call for questions from the audience, but we'll just be here and you can ask. But
No, Ren, we will actually call for questions from the audience.
Oh, you are?
I'm up here to
Okay,
call
that's
for
what I
questions
thought
from
you
the
were
audience.
doing here. So, okay,
Yes,
okay,
I'm
so-
not the Grim Reaper.
Oh,
I am the
you have a look at the Grim Reaper.
enabler.
You look just like this Bannon guy on Saturday Night Live over there. Okay, so then I'm really happy.
I'd like to say that my students have told me that I look like Mark Hamill at the very end of The Force Awakens. I'm him rather than the other guy.
Okay.
Anyway,
So I'm glad we will have questions. So I'm so glad.
we'd love to have this conversation going, but I think we'd love to have some questions.
Okay, great.
as well. So
Great. So let's.
we have a microphone right here, and I'm going to start right there.
I think a really simple question. Most of the planets don't have perfectly circular orbits, but you represented them as though they do. And I wonder if that's taken into account in any way. And also, I don't believe it's correct that all planets orbit on the same plane around the sun. And I wonder if either of those, do they factor into your model somehow?
Yes. No, I circularized the orbit. We call the average orbit the semi-major axis. And
That's
what
the
I'm,
average of the ellipses.
Right.
And it's a term that's always used. It's the semi-major axis. What is the average orbit?
So that's what I'm dealing with. Kepler, on the other hand, in fact, the music that you see here, that's Johannes Kepler, and he did take that into account, and he discovered that the elliptical orbits of the planets, which he discovered, have a musical coherence to them in terms of the various speed that the planet moves, faster when it's closer to the sun, slower when it's further away. The Earth has a very smallly elliptical orbit. It's almost circular. But nonetheless, musically, it produces the two notes, do, re, mi, fa, sol. It produces the two notes, mi and fa, and Kepler noted, this is perfectly appropriate because here on Earth there is misery and famine.
That's apophenia. But what, I will ask about, I just want to say that, by the way, another way of thinking about this is if you think of a roulette wheel, you can do this, it's a circular wheel, you can figure out what the radius of it is, but within the roulette well, the marble goes up, it comes down, it goes up, and it's elliptical, but you could still have a number for that, the circle. He asked you about the different orbits.
Yes, they are all slightly tilted relative to the other. Pluto very much tilted. The strange thing is that the sun is tilted 7 degrees relative to them. And nobody has a really good explanation for that. It would seem that if you have an orbital system, all of which descended from the same cloud, that the general plane of the planets would match the center plane of the sun's rotation, but it's not the case. There's a cocked hat effect that we don't really have an explanation for. Some people are now saying that the theoretical Planet 9 way out is exerting a cantilever force on the planets and tilting all of them relative to the sun. But we just don't know. It's one of those mysteries.
But we do see, you know, planets in formation where basically the plane of the disk is actually misaligned with the rotation of the object, even very early on
Right.
in formation. So we see signatures, and yes, you're absolutely right that this is sort of like a zero order ordering, but of course you have to take into account, you know, inclination and eccentricity too.
Yeah, hi. Do you have you looked to see, or do you have any evidence that these patterns apply to other physical environments like fluid dynamics or subatomic particles? Or, I guess a broader question: is there any type of empirical study you could do to prove this in other areas?
I don't think so. I mean, the orbits, the electron orbits around the atom follow a very different formula. Here, this is 2 raised to various powers in the orbits of the electron, and as you understand it, it's various integers squared going out.
Yeah, although we think of them not as orbits,
Yeah,
but as
not real
statistical
orbits, but
distributions.
orbital clouds. So no, I haven't gone into other systems. I'm just.
But the hierarchy of atoms, it will be interesting to look
Right.
at and see,
Right.
and they're very diverse.
Another question?
Up there?
Up there, maybe there, well.
Start here on that? Okay, why don't we start with you, and then we'll come over to you next.
So my question is actually, I think it's for Ren Weschler, but it's inspired by one of Walter's great works, The Conversation. I'm interested in how, as an observer of this conflict of the faculties over many years, Ren, you see the problem of discipline, or as you said earlier, caste. I know from the book that some of the professional physicists regard Walter's work as something like a conspiracy, or it's numerological, so it relies on some grand design that is in some ways mythical or fictional. But I can imagine that from the perspective of an amateur, somebody who is trying to produce an out of left field jolt to the professional discipline, that the discipline looks like a conspiracy as well. It looks like a kind of agreement to exclude outsiders. So what is your sense? What have you learned by watching this conflict?
I mean, it's something that I come upon all the time, and it's one of my favorite subjects in other books I've done, which I would describe as who gets to say and who gets to say who gets to say. And in some ways, taking what you're saying even further, the best criticism I heard against what Walter was doing is if you allow this kind of thing in, you're letting climate change deniers in, you're letting if you're not going to take the rules of science seriously, in an ironclad sort of way, they are there to protect us, and if we're not going to agree at least on those base things, you're going to, before you know it, have vaccine deniers and and so on and so on. And for myself, I want to entertain both the absolute agreement that is a danger. Walter would say that's a danger. We all say that's a danger. And yet know that in the history of science, in very interesting ways, This has happened, and it seems to be possible that an intelligent person can keep several ideas in their head at the same time. A very good example that I use that toward the end as, to my mind, the strongest argument, and a very passionate argument by Lee Smolin, it happens, where he's saying we just have to have these rules and you just can't be breaking them. But then I follow that exactly up with an account of Alfred Wegener, who was an outsider. He was a meteorologist, for God's sakes, who in 1905 came up with the notion of continental drift. And he had no idea why it was happening. The geologist said this, in other words, the idea that the shoulder of Africa, or that the nose of Brazil hits the armpit of Africa, you know, that whole thing. And he did it through a whole set of observations that were kind of uncanny. That there were fossil fields that were in South America, and they matched up perfectly where they would be there. That there were underneath glaciers, there were evidence that there had once been tropical forests. He had built up all these things, and he got beaten up. And the language that was used against him was very, very similar to some of the language that we'd found earlier in the book against Walter. Well, what's your proof? You know, these are just observations. This is anecdotal. It doesn't fit in. And it wasn't until years later, by the way, it was in the 50s, and somebody should go do this study in exactly the same way that Franklin is the person who did the real important work just before Crick and Watson. There was a woman who did the real important work at Columbia just before the men who took credit for continental drift. In the 1960s, only in the 1960s that becomes accepted, and it becomes accepted when an outsider says these things. It's not accepted, and it's partly because there hasn't been a thing that explains it.
The stumbling block was what mechanism can allow continents to move about.
And you're being asked what mechanism allows this, and you don't have an answer. But so anyways, I was telling Chancellor Blumenthal that when I teach my class, my motto is receive them ignorant, dispatch them confused. and I hope that at the end of my book you are confused in a really clear way.
Okay, we're going to do Peter there, and then we'll come over to you.
Oh, hi, Ren. One of my favorite astrophysicists is Lisa Randall, who was the first to report out on the Higgs discovery in 2012. And in her book, Warped Passages, she uses song lyrics to head up every chapter, and she has a running story between characters who have different dimensions. And so she'll explain a physics principle by saying that this guy who likes fast cars and gambling had left his car open, and this other woman who owns owls, one of her owls pecked the leather on his chair, so he wants her to get rid of all her owls, and she said, only one did it, but I don't know which. So, and she's incredible about explaining these kinds of things and doesn't get off on these far things, but she entertains ideas. And so I've been kind of following her and reading a lot of stuff and your stuff too. So I just wanted to let you know, metaphors and entertaining ideas, there are some physicists, I'm sure you know, in there who are quite good at that kind of stuff.
Yes, I just read her book, Dark Matter and Dinosaurs, and she's attempting to prove a link between the orbit of the solar system in the galaxy kind of going through and coming out and going through a disk of particularly dense dark matter, all hypothetical, but as it goes through the disk of dark matter, there are gravitational perturbations in the Oort cloud and the Kuiper belt that cause comets and large objects to get detached from their orbits and start to plunge inward, and on a period of every 32 to 32 million years. And one of these things might have been have produced the asteroid that killed the dinosaurs. So very provocative work, but very readable.
Walter, first of all, I love your observations on music and the universe and so forth. I love that kind of stuff. And but your illustrations have placed the major orbits in Western musical tonalities. Have you looked at the minor or the in-between orbits and how they might relate to non-Western music? the quarter tones and eighth tones.
He's saying that you have placed it in Western octaves. Have you looked at other kinds of octaves?
No,
On the smaller and the
I-
other elliptic, other orbits.
Was that the question?
And would some of the other things be in different kinds of octaves? There are different Eastern octaves and so on.
Renegades.
Where the renegades go into Eastern octaves, for example.
Actually, the renegades fall within the musical harmonies. I didn't get to it, but it's in the book. Uranus is, in my scale, G. Pluto is G, but Neptune falls neatly at the midpoint for D. And if you play G, D, G, it's a very pleasant
And it sounds
sound.
like God. But one of the main points is that he's claiming that it is not the Western octave.
It's not even human.
That this is the octave that would be produced by a pebble hitting Mars, and the gong that Mars would make with a meteorite hitting it. It is a natural phenomenon.
So we're going to take one more question, and then we have a book signing.
Yep.
So you'd be able to perhaps ask the question directly. So we've got the gentleman back there, and I apologize to others who didn't have a chance.
I wonder if this is a situation of our present time. If I recall, it's expected the moon will come closer to the Earth because of tidal drag eventually. Perhaps if there are tidal drags in all of these orbits will change. It seems inconsistent that the moon might change its orbital distance and still fit some kind of schematic, whether it's understood yet or not.
Did you hear basically that where things are right now is where they are in the present time, that they could all move around and so forth?
Right.
And your thought about that?
Yes, and that's what we're finding when we look at exoplanets, that the planet, the system that I started with is only 30 million years old. The solar system is, we think, 4.5 billion years old. So that's a newborn system, and we are looking at it in a flash of time. And what's fascinating is that before we started really getting into detail with exoplanet systems, which was started about a little over 20 years ago, we could have thought, well, we'll just find pretty much duplicates of our solar system out there, but that's not what we found. We are increasingly, the more we discover, the more we see how unique our solar system is. That the first planet is very far away from the sun compared to other planets. Some suns have what are known as hot Jupiters, massive planets orbiting in 4 days around the star. But here's Mercury, very far away from the sun in terms of the diameter of the sun, and way out is Pluto. So that seems to talk about the stability and to a certain extent the habitability of our solar system.
Did you have any last comments?
I think it goes back to the question that we were talking about, we're really seeing things in snapshot in time,
Right.
and we're really looking at things that are able to survive versus things that are not. And I think you make a very interesting point that the orbits of the solar system are constantly changing.
Right.
I think your broad perspective is that they may be these caustics in which things accumulate, which are not very precise, and
Right.
whether or not those sort of caustics can evolve from a self-consistent theory. And I think that's the question.
That's
I
the
think is very
cafeteria
interesting.
conversation. Before you sign us off, I just want to say one thing very quickly. This is a good book. I like it. I love it. Anyway, but the point is, do not buy books on Amazon. The books need to be bought at either independent bookstores or campus bookstores or these sorts of places, art museum bookstores. These are the spine of America. So I urge you, if you're thinking of buying it, buy it here, for example, at this bookstore. But I'll give you an even better reason, which is, do you have it on you?
I have it in my bag.
He'll get it from his bag. Walter had decided when we were going to go on a book tour that he would take his little fortune cookie things and turn them into bookmarks. And there will be a whole little range of them right here, and everyone who buys a book gets to take one, and it will tell you the truth about your life.